Okay, welcome all, and welcome to those who are watching this as a recorded video. Um, Let me share my screen and we'll talk about what the plan is today. Okay, the plan is, as always, we'll start out with any questions you might have, and that's always what I do. And then after that, we're going to talk about confidence interval for a mean. We're going to do a little exercise. I'm going to do a survey of you all. It's one of my favorite surveys to do. And hopefully you'll be honest, but if you're not, that's okay too. And then after that, we'll go over a confidence interval and we'll talk about t-interval. We've had a lot of distributions in this class. So we've had a binomial distribution, a uniform distribution, we've had a normal distribution, and today we're going to have a new distribution called a t-distribution. And we'll talk about what that means and what it's about. And then talk about interpreting the confidence level. So number 2 is really understanding confidence levels, intervals, and kind of giving interpretation of the interval. But then we'll also talk about the level, and that may not mean anything to you right now, but by the end of the hour and a half, it should. Then we'll go over a confidence interval for a proportion. I have an example, a news article. I like to do news articles if I can. And sorry if I do a lot of politics, but there are so many easy to find surveys on politics. But there's this confidence interval stuff is done in just about every field. But we'll do a confidence interval to see how much people approve of Biden's work, since Biden's our new president. And we'll check that out. Okay. Just a note, in terms of politics, I never get political. Okay. Even when I ran for office, I didn't even tell anyone I was running. But I can read articles. That I can do. So then what we'll talk about is sample size. So we've already said that you need for a mean over what number? Do you remember?
30.
We need over 30 to do anything. Because if you don't have over 30, you don't have a normal distribution. If you don't have a normal distribution, it's just all guesswork. It's silly. So, but if you have over 30, it still may not be enough to have a small enough standard error. Because if you have a big standard error, then you're not really learning much about what you're trying to investigate. So we'll talk about what sample size do you need to make sure that the standard error, and even more in particular, what's called the margin of error, is small enough. And we'll get into that. And there's a formula for that. And there's also a calculator for that. And then we'll talk about the sample size for a proportion. So same idea is that if you're doing a yes or no survey and you want to say, well, how many people do you have to ask? So what do we say to even do anything? How many people? To use a normal distribution? And it's not just a number on this one. Who remembers? This was last week. Nobody remembers? NP and NQ greater than 5. So it's 5 yes and 5 no. And actually greater than 5 yes or greater than 5 no. So 5's not enough, 6 is enough. Okay, in our class. And by the way, what I've decided is I set the benchmark. It's kind of the most common. It doesn't mean that that's some fixed number. But if I start changing it every other day, I think you'll get confused. Do you agree? So in our class, we'll keep it at over 5. Some people keep it, say, over 10. But it doesn't really matter because in the real world, we're going to find out to have a good estimate of something, it's going to be much bigger than that. Much bigger than 5 yeses and 5 nos. And we'll see that and we'll understand, and I'll have, like I said, talk about what we might need. Okay. So that's the plan today. Are there any questions about anything that you want to hear about? Not hearing any. Okay, just let you know, we're kind of at a downtime, as in like down as in not stressful time, because the test is over. The project, which I might talk a little bit about today, the project 2 isn't for a long time. Exam 2 is not for a long time. We're still doing important content, but there's no major like assignments that affect your grade in a huge way in the next couple of weeks. That's just a note. I do want to mention one more thing that I forgot to mention, and that is a week from today is not going to be the webinar, even if it's requested. And how come?
President's Day.
Yeah, President's Day. So I like to honor the holidays. So that I'll still answer emails. I'll do that, and because that's okay. But if I'm not around for a few hours, I'm probably skiing. But it's President's Day. So, but I won't do a webinar on President's Day. I don't think that's right. I think we like to honor the holidays.
Are we doing one for that week?
We're doing the Tuesday. Yeah.
Tuesday.
But if there was a request for Monday, I'd say no, because I don't want to do a webinar on Monday. Does that make sense? Because I want to honor the holiday. If there was a request for Tuesday earlier, I could do that, but not Monday, because that's a holiday. And Friday also. Not that we have anything Friday anyway. But just to note that we get the long weekend this coming weekend. I like to honor that holidays.
I didn't see what time on Tuesday.
6 o'clock. Always 6 o'clock. The set time is always 6.
Okay.
Yeah, and if you can't make it, then you can post on the Q&A a time that you could make it, but not Monday, because Monday's again, I want to honor the presidents.
I'm all for that.
Yeah, so that's just my feeling, and I think I could get in trouble actually if I had a webinar, so I don't want to do that either, because we're not supposed to be in session on Monday. So that's just another note. I mean, if you want to do some Canvas work and study, that's up to you, but it's not required. Okay, so no questions. Okay, so I have a question for you. It's one of my favorite ones to ask, because I've actually watched things change. I forgot to erase the last webinar. And here's my question for you. How old were you when you experienced your first passionate kiss? Okay. By the way, if you say 6, someone needs to go to jail. So I want you to post in the chat box. And again, this is a chat box. It doesn't get posted on YouTube or anything. And if you don't want to tell the truth, you can just put a number up there. But most people are okay with it. Okay. And I've been doing this actually for a quarter century, and I've watched it change. Okay. So I'm going to put in the numbers. So 13, 15, 14. 16, 14, 17. 21. Okay, and that might be the group. No, 19, still got him. Yeah, this isn't supposed to be a hard question. Most people remember their first kiss, maybe not, but maybe you were too drunk or something, but probably not. Okay, so we just did a survey, and I want to let you know, is this a big enough sample size to do anything reliable?
No, but it depends, I guess. What?
No, it doesn't depend. This is not a big enough sample size. Okay, we have a sample size of what, 2, what is it? 2, 4, 6, 8. Okay, which is all we're going to get today, because that's what we've got here. So it's not a big enough sample size, so you're going to have to live with this. I will tell you that if you ever do real research, like if you're like getting a master's degree and doing research in your field, do not ever do any statistics with a sample size of 8. Okay, it will never get published, and it's just wrong. So this is just a class experiment. So I just want to give that big disclaimer. Any questions on that? Okay, so here's a question. We can pop this in if you want pretty easily. I'm going to copy this and I can go into, let's see, got to grab the right one. I got a few of these. Yep, this one. And in fact, we can get the statistics pretty easily. This is a sample. I can calculate it. Okay, and notice our mean is 16, about 16.125. Okay. So what I want to look at is the following. Let me write this down. So our mean, and by the way, what letter do we use for this mean? What symbol do we use for the mean?
Mu.
Not mu. Good try, though. It's definitely not a mu. Mu is a population mean, and I don't know the population of all, let's call our population all online statistics.
Oh, is it N? Is it?
Now, N is 8.
Oh, what happened to you?
N is 8, right? Because N is the
S?
S is standard deviation.
Would it be mu x bar?
You said it, but you said too much.
X
Yeah, there we go. Yeah, now you said it. X bar. Okay, so X bar. And be patient with me. Takes a second to get the bar over it. I think it's that one. There we go. So X bar, I'm going to call it 16.1. Okay. Most people, except when you're having it, don't care about more than one decimal place. Do you agree? This is early after your 16th birthday. Okay, now here's a question. How reliable is this estimate for the population mean? Do you understand what I'm asking?
I guess there could be some biases.
There's some biases, but I'm worried about something else, and that we have a small sample size. So the question is, do you think it's likely that the mean is, say, more than 25? Based on the fact that we took a sample of size 8 and we got 16.1 for X bar.
No.
Okay, probably not likely. Okay, and I'm going to assume that the population distribution for first kisses is normal. Otherwise, we can't do anything. Remember, because the sample size is 8. If you don't assume normality, forget it. Does that make sense? Okay, so it's probably not 25, because if we got an X bar of 16 with a sample size of 8, then I know it's not a big sample size, but you probably isn't 25. But would you be real confident that it is like between, say, 15.9 and 16.3? Do you think that you're real confident about that? So what range of values might you be confident to say that you think that this is when the age of first kiss is? Any questions on that idea?
Can you rephrase that question? Sorry, my son is.
Okay, so what range of values, and 16.1 would be the center of your range, would you be confident saying that you're pretty sure that the age of first passionate kiss is between those values? Okay, so for example, if I said 0 to 32.2, I mean, you're like 100% confident, right? Okay, but if I said 16 to 16.2, you're probably not that confident. Do you agree? Because we only had a sample size of 8, and how reliable is a 16.1? Does that make sense? So that's what today is all about, is to talk about what's called a confidence interval. And what we can do is we can say that if we've assumed we have a normal distribution, we can use the central limit theorem and say that, well, our best estimate is 16.1 for the mean. Is that clear? Given that we're assuming this is unbiased, and it might be biased, but I'm assuming it's unbiased. So our best estimate is 16.1. But what range of values, how far out could you go so you're, say, 95% confident? And the idea here is we can draw a picture. And what do you think the picture is going to look like? I'm hoping you all know. It's a picture we always do.
A rectangle?
What did I assume the distribution was, remember?
Oh, I didn't hear that. I'm sorry.
Yeah, bell-shaped. I like what you said, bell-shaped. So the idea is we can draw a bell-shaped curve. I'll do my best and hopefully this works. I'm never the best at scribbling with the mouse, but not too bad, right? And then we know that right there, at least our best guess, I need to go. Let's try again. There we go. That's not letting me scribble. Ah, there we go. Kind of. All right, right there is our best guess for the mean, which was 16.1. Any question on that idea so far? Now, if we want to be 95% confident we're right, what we can do is we can draw more and go over here and over here. And say that this area in here is 0.95. And then these values to the left and the right, whatever they are, will be that interval that you can say you're 95% confident it's between. Is that clear? Okay, and notice when we did the calculation, I think it was that one, standard deviation was about 2.7, but that's not the standard deviation for the sampling distribution. What do we have to do? Think about last week.
You have to divide it by the sample size, right?
The square root of the sample size.
Square root of the sample size.
Yeah, so if you take the 2.7 and divide by the square root of 8, that gives you pretty close to 1, actually. Square root of 9 is 3. 2.7 over 3 is a little less than 1. So it's going to be just pretty close to 1. So that means that we can guess that if I go back, that this number here is probably going to be around 15. This one's going to be around 17. Do you see that? And that is going to be the interval that we can be 95% confident that the age of first passionate kiss is. Any questions on this?
Yeah, is it always 95%?
That's a good question. The answer is no. But I'd say most of the time it is in the real world. Okay. And I don't know if I've mentioned it, but I've done some consulting work, mostly so I can keep up with statistics and see what's going on. And when you're consulting, by the way, if you ever do consulting, your client is the one that tells you what they want. And I consulted for the Forest Service, once, and they wanted 90%. And you know, the rule, the boss is always right. So I did a 90% confidence interval for them. If it's social science, I don't know what your major is, but if you're doing social science, it's always 95%. So psychology, sociology, always 95%. News, always 95%. So media always done 95%. Okay, some science does more or less. So notice that if you have like a 99% confidence instead of a 95%, then you'll be more confident, which means that there's a less chance of being wrong. Does that make sense? Okay, which sounds good, right? But you'll have a smaller chance of being wrong, except you're going to have a wider interval. Like I could be 99.999% confident that the average age of first kiss is between 0 and 90. I bet you all can be the same, right? But how useful would that be to say that? Nothing. If you told people, I just found out the average age of first kiss was between 0 and 90 years old, they're going to look at you and say, yeah, I kind of knew that. Do you see that? So you want a trade-off between the confidence level, because you asked a really good question, and what's called the margin of error, which is how far you are from the middle to the end, to the edge. And you want to make sure you have a margin of error that is useful, but you also don't want to have such a low level of confidence that you're probably wrong. Do you see what I mean? In our class, just because I try to make things so that I don't change every other day. In terms of examples, I will always give 90, 95, and 99. The only time I'll give anything else is if I ask you to compute something, just to make sure that you know how to compute with a different number, but not for any kind of true example. So 95% confidence is standard. 90% means that you have some flexibility and you're going to have a kind of a better statement about the where the range is. 99% means you're more sure that you're right, but your range is going to be wide and maybe crummy. Any questions on that? So let me continue on this. Question? So let me continue on one more thing that's important for you all. Very important. A lot of people have trouble with this, and that is project 2. I know it feels like you just did project 1, but it's time to talk a little bit about project 2. Guess one of the main things you're going to have to do for project 2. Any guess?
Confidence intervals.
Exactly. Actually, confidence interval. You can do a single confidence interval. And what you're going to do is you're going to look at 90, 95, and 99. You're going to look at all 3 of them and decide which is best. And write about how you decided. Does that make sense? So that's something you're going to have to do in project 2. Okay, again, we're not ready to talk about all the details of project 2, but I can start telling you some of the things. Any questions on this idea? Okay, now I'm going to do something that may not work, because sometimes it kills me, and that's save and close, and sometimes it dies. It died. Come on. I hate that. For some reason, it doesn't save and close. All right. We gotta start over on this guy. All right, we're gonna leave that. We're gonna lose that picture. That's what happens when, for some reason, it doesn't save and close when I'm on Zoom. But hopefully, y'all remember that picture, because I think the picture is kind of not really there anymore. Let's try one more thing. Let's just get rid of it. Okay, but y'all saw the picture. Okay, so that's the picture. And again, you get a confidence interval. So there's a lot of things here. One is when we do this confidence interval, one of the problems is we need to write down what the standard error is. Is that clear? To draw that picture. But why can't I truly write down the standard error? Why can't I use what I got and say, hey, I know my standard deviation is 2.7484. What's wrong with that? And then divide by root 8. There's a mistake in doing that. Anyone catch the mistake?
Because it's not the standard deviation for the sample size.
The first 5 words were perfect. And then for the sample size wasn't so good. It's not the, what kind of,
Population mean,
it's not the population, not mean, but
standard deviation
It's not
for the
the population.
population size.
it's not the population standard deviation. Okay. So the problem is that this doesn't work if we wanted to find the standard error, because we don't know the standard error, because we don't know the population standard deviation. And it turns out, it's kind of cool. There's some cool history on this. This was discovered by a guy, Fisher, in 100 years ago or so, something like that, because of beer. I know that's what you're all thinking. Had to do with beer. He was actually working for a beer company, and he was running statistics for the beer company. And what he realized is that his calculations weren't right 95% of the time, which they should be, based on the picture, right? And what he came up with was the fact that he was using the sample standard deviation, and there was an error. So then he was a mathematician, and he did some very intense mathematics and came up with a new distribution that allowed him to deal with the mistake, that fudge factor of using the sample standard deviation when you don't know the population standard deviation. Does that make sense, that there's going to be an error? So what he came up with is a new distribution that dealt with that fudge factor. And he also was a professor, and he named it after his students, and he called it the students' t-test. We usually just say T, but he called it the students' t-test. So I have a picture of the students' t-test, and by the way, it turns out with a very large sample size, there's no problem. Because with a very large sample size, the standard deviation is probably going to be the same for the population in the sample. Does that make sense? But for a small sample size, you got a problem. So I actually wrote a program, because I'm a mathematician also, and it's this one. So what I did is I created a slider. So if we have a sample size of even 25, you can see that we have 2 curves. Okay, the black curve is the normal distribution, and the red curve is the student's t-distribution. And take a look. Do they look the same, or do they look real different?
They're the same, right? Or am I missing something?
They're not the same, but they're off by like 1%. Maybe. So for our eyes, it's hard to see that there's a difference. But now let's drop the sample size. Okay, so if the sample size instead of 25, let's go down to 10. And do you see now they're changing a little bit? Now there's a bit of a difference. Do you see that? And if we go even much less, like 5, now you can see that there's actually a pretty decent difference. Any questions on that? So it turns
Which
out—
one is red? Is that the student's T distribution? Is
Yeah.
the red one then? Okay.
Yeah, the
thanks.
red is the student's t-distribution. It's a little more spread out than the normal. Okay. And if I go to like just a few, like 3, then it starts getting very different. Do you see? But as soon as you get, I don't know, over 30 or so, it probably doesn't make any difference. You probably can't see the difference. Do you see that? So once you get large, like over 30, they're basically the same. In the old days, we used to use the normal distribution to approximate the t-distribution. And now we don't need to anymore. Do you know why? When I first taught this class versus now?
You have a calculator for it?
Exactly. Okay. And by the way, I'm not the first one to program it, but the point is when I first got this class, those calculators, like nobody had them. So, but now we got calculators, so we can really use the student's t-distribution. Any questions on that? Okay, so that's the first thing. All right, so everyone understand the picture and kind of how this is all working? All right, what I'm not going to do is I'm not going to have you do all the mathematics. That's not your job, that's my job. Sound right? But I do want to find out what those bounds are, the left and right bounds. So, as you might have guessed, that one. There's a calculator for it. Okay, and this one I did code. Am I the first one to code? No, but I made sure that it works for our class. And let's see if you guys can guess which one we're going to use. What number?
Number 9.
Number 9 is a good idea, but we don't have to with this example. We could do number 10. And that's because we have data. Do you see that? So we have data because we have those eight values. So with this one, I can just put in the data, copy paste. And maybe 95% for our first confidence level. What do you think? Are you comfortable being 95% confident for something like this? And my feeling is yes, this is social science. Any questions on that? No one's going to die if we're wrong. Do you agree? All right. So if we're wrong and someone's going to die, then you probably want to go like 99.99 or some intense confidence level because you don't want to be wrong. But on this one, it's just social science. It's fun. Any questions on that? So I'm going to go 95%. And let's calculate. And by the way, the calculator also gives you X bar and S because those are important numbers. But more importantly, we get our lower bound and our upper bound. And the lower bound is 13.8 and the upper bound is 18.4. Okay, notice it's pretty widespread. And in fact, it's really easy to change that. If you wanted to be a little less widespread, would we make it 99 or 90? If you wanted a narrower spread.
90.
90.
90. So let's look at what happens if you make it 90. Do you see it got narrower? 14.2 to 18. So, that gives you a little better information. Any questions on that? Okay, so maybe for this example, 90 might make sense since we have such a small sample size. Do you see that? We don't have any confidence about anything anyway. So I'm going to just use 1 decimal place of accuracy just because that's good enough for my life. I don't know about you guys, but I don't really care about 2 decimal places on age of first gifts, on average age. So it's 14.3 to 18. So let's try, and it's 90%, so let's write that in. Okay, and there's our 90% confidence interval. Anyone lost on what I just did? Okay, now it's time to interpret the confidence interval. Okay, which is also state the conclusion. So there's different ways of asking the same thing, so get ready for it. And it's pretty easy, but you want to get used to it. And by the way, and I'm not sure if you've read some of my comments on your test yet, but I think I told you more than 3 times that for the expected value interpretation, remember do you remember that I told you that there were words you had to have in there? And I don't know what to do to make you guys to put the words in, but half the class didn't put the words in that I told you had to put in. Okay, so for the expected value, you had to have many, likely, average, and close to. Do you remember that? If you didn't, you lost points, by the way. And I promise that. Okay, on this one, and this time, sometimes it helps you get going, especially the next exam when we have a lot more stuff. The first word is very important, and it's very easy. It's not a math word. Can you remember that word? With. And if you put that word in, then you're getting started. And most people that put that word in actually get it right, get the whole thing right. But if you don't put that word in, you're screwed. Just let you know that. So now let me put more words in. So with 90% confidence, the population mean age of first kiss, not kill, kiss, is between 14.3 and 18.0 years old. So I want to give you one more thing that I want to note, that you will lose points if you don't put it in, and that's the word population. So the word population must be in the interpretation. All right, let me get there again. There we go. So the population mean, that we know we're 100% confident about the sample mean. That's 16.1. Is that clear? What we don't know is the population mean. And will we ever know the population mean? No, it's not possible, right? You can't ask everyone in the world, okay, or in your whole population. But we can get the sample mean and use it to get a confidence interval. Any questions on the idea? Okay, so notice, by the way, we can say high school. Do you agree? That's high school time. 14 to 18 years is high school. Okay, and are you surprised about that? Okay, just to let you know, my generation, it's not. Anyone know what it was in my generation?
College years.
No, we had more fun.
Nice.
No, my first kiss, I was 13, and everyone laughed at me because I was so old. And that's just how it was in those days. Yeah, nowadays it's gone older and older and older, and it's just everything. So and I've read all the statistics on this, not just first kiss, but loss of virginity, first boyfriend or girlfriend, first child, first marriage, everything is getting older. Okay. And don't ask me why. I'm a statistician. I can see the numbers. I'm not a psychologist or whatever, but I've seen the numbers. Okay, and I've definitely watched it change over my career. Any questions on this? It's kind of cool. Okay, there's no questions. Let me say, what does it mean to be 90% confident? And another way of saying that is interpret the confidence level. Okay, notice that's a very different question than interpret the confidence interval. Don't get them confused. Any question on the question? Okay, so what I'm going to do is I'm going to show you another activity that I created. as you probably figured out, I'm a programmer. And I created a visualization of confidence levels. So this is an example, and what it's going to do is when you change the confidence level or the sample size, it will generate a whole bunch of confidence intervals. So it'll take a whole bunch of random samples and find the confidence interval for that random sample. Okay, so notice for this visualization, 0 is the mean. And if you look at this, are all of the confidence intervals that got generated randomly, do they all contain 0?
No.
No, look at this one. This one doesn't. Neither does this one. Neither does this one up here. How many would you expect to contain 0? What percent for this example? Whoops, just moved. Okay, and the idea is if you change the confidence level to, let's say, just for fun, 63%, then you would expect about 63% of the confidence intervals to contain the population mean. Whereas if you use, say, a 90% confidence interval, then you expect 90% of the confidence intervals to contain the population mean. Any questions on that? Okay, regardless of the sample size, by the way. Changing the sample size is going to change the width of the confidence interval. So if I have a very small sample size, like 3, look how wide these confidence intervals are. Do you see that? Whereas if I have a sample size of 68, they just got much narrower. And that is because of the central limit theorem. Because remember that the standard error is divided by the square root of the sample size. So if you change it from, say, 10 to 100, let's say you change it from, say, 3 to 12. See if I can get to 12. Then I am going to cut the width of the confidence interval by a factor of 2 because I've multiplied the sample size by 4, and the square root of 4 is 2. Anyone lost on that? But the confidence level tells you that if you're going to be doing a whole bunch of confidence intervals, that's the percent of them that will contain the population mean. So if you're in the business of creating confidence intervals and your standard is 95%, then 95% of the time, your statements are going to be right. And 5%, they're not going to be very good confidence intervals because the mean's not even going to be there. It's going to be outside of it. Do you see that? And you have to decide for yourself, what percentage of the time are you okay being wrong? Any questions on this idea? Okay, but again, if you have a very, very small confidence level, like 99%, a very high confidence level, then you get a very wide confidence interval. Whereas if you drop the confidence level, confidence intervals get very narrow. So it's a trade-off. Any questions on the idea?
I'm kind of confused why there is so many confidence intervals.
Because I programmed them. There's an infinite amount of possible confidence intervals because you can do samples of size 12 a million times if you want. And each time you do one, you can get a confidence interval. Do you see that? So what I did is I coded the computer. How many is this? 1, 2, 3, 4, 5, 6, 7, 9, 11, 13, 14, 16, 18, 20. So I coded the computer to do 20, to grab 20 samples. Do you see that? Of size 12, because that's what I set it at here. And for each sample, you're going to get a different confidence interval. Do you see that? I could have coded it to be 4 if I wanted to, or 1,000,000. 1,000,000, it would get really busy and it would probably take forever for it to actually generate. Does that make sense?
Yeah.
Yeah, so the reason why there's so many is I coded them. And in the real world, you usually only do one, except that if you're a researcher, you can be doing a lot of times with different things. And if you're wrong a lot, you're going to lose. What's going to happen if you're wrong a lot to your career?
You'll lose clients.
You're going to lose clients, or you're going to lose credibility.
Lose credibility.
Yeah, bad stuff is going to happen. Do you see that? So you want to make sure that you have a pretty good level of confidence. And the standard is 95%. That's the standard. Okay. And by the way, the standard was set. It wasn't a mathematician. Okay. It was set by the news agency in the 1930s. Anyone know who that was? Give you a hint. It was not online.
The Hearst.
A good guess. New York Times.
Mhm.
Yeah, the New York Times is the one that set 95%. And since they did it, they got the presidential election correct when everyone else was getting it wrong. Then everyone believed them, and now it's gone. That's what everyone uses. So that's the history of that. Okay, any questions on this? Okay, so let me type this out. So now I can answer the question. We can say that if many samples of size 8, because we did a size 8, were collected, then each would produce its unique confidence interval.
Can you scroll up a little bit, please?
Yeah, sure. Thanks for asking, because what I see is not always what you see. Okay. And then 90, because we're doing 90% for this one, 90% of these intervals will contain the true population mean age of first kiss. Any questions on what this says? I will let you know there is no short way of interpreting the confidence level. Don't think you can. And if you do it in a short way, guess what's going to happen on a test?
Lose points.
You will lose points. Okay, so you want to get used to this kind of strategy. Okay, and this is kind of a template. And you'll see on the discussion post, I used basically the same template, very similar. Any questions at all on this example? Okay, so now let's do another one. Okay, but now I'm not going to be doing means anymore. Let me go to a news article. And I'm using Gallup. Gallup tends to show the statistics, so I kind of like Gallup. There's some others that do it also. And the article says, Biden begins term with 57% job approval. Do you believe that? Do you believe that the job approval of all Americans is exactly 57%? What do you think?
No.
No, because they didn't ask everybody,
Yeah. How do you know they didn't ask everyone?
because it's impossible.
They didn't ask me.
There you go.
I wasn't asked either.
And I wasn't either. And by the way, I've been teaching this for a long time. I've never had anyone say they asked me. So it's never happened. And again, that's because there's 300 and some million people in the country. So the chance of one of us getting asked is really small. Okay, so they didn't ask us. They don't know the exact number. So the question is, Do you think it's close to 57%? Do you think it could be, say, 80%? What do you think?
Probably not.
Probably not. Not if they did their job right. Okay, so now I'm going to scroll down and get to their details. And this is the survey methods, which you've seen, some of you have seen if you've looked at some of the discussion posts, because some people have used Gallup also. But now we're going to read a little more and understand a little more. Okay, so again, what we've seen, one thing is they did a sample. I don't believe it was random because there's voluntary response bias, but they can say what they want. But they surveyed 906 adults, certainly enough to use the central limit theorem and to say we have a normal distribution, because 906 times 57% is way more than 5, and so is 906 times 43%. Is everyone okay with that? So remember, there's yes, no question. So we're talking about NP and NQ greater than 5. Okay, so no problem. But now we can read a little more. For results on the total sample of national adults, the margin of sampling error is plus or minus 4 percentage points at the 95% confidence level. Now, do you see why I like Gallup? Because Gallup says it right. Okay, so hopefully at this point, you know what 95% confidence level means. Do y'all know that? The margin of sampling error is plus or minus 4 percentage points. What that is how far from 57% the left and right sides of the confidence interval are. So in particular, we can now state the confidence interval. Okay, so let's write this out. I need.
When you read that, does that mean it's like 91 and 99 or no?
So we're
That-
not changing the confidence level. We're changing the 57%. So let me write down what it is. I'll answer your question. So with 95% confidence, remember, it always starts with the word with. And now it's not a mean, is it? Why am I not going to write population mean?
I can't
There's
see
a
the
sam-
article anymore, sorry.
Okay, here's the article.
There's a
And the
sample.
title is what we want, huh? So why don't I write populate? Right, it's it's not a portion, but it's a proportion. Proportion. So it's a proportion. It's a yes, no question. With yes, no questions, we don't have a mean, we have a proportion. Is that clear? So the population proportion of all Americans who approve of the job that Biden is doing is between, and now it's 0.53. How did I get 0.53?
Minus 4% from the 57.
Exactly. 57 minus 4 is 53. And 0.61. Okay. You can also say that there's another way of saying it, 95% confidence between 53% and 61% of all, notice word all, that has to be there, Americans.
Can you scroll down a little bit, please, again? Thank you.
All Americans approve of the job that Biden is doing. Any questions on the confidence interval? Any questions? By the
Could
way,
you
I'm always,
instead,
huh?
I'm sorry. Could you, instead of putting between 53 and 61%, could you just do the 95 with the plus minus 4%?
You can, but I think it's harder to understand what's going on.
Okay,
Most people don't know what that means. Do you agree?
right.
Whereas this is very clear to read, isn't it? Somewhere between these percents. We don't know exactly the percent, but it's gonna, but with 95% confident, it's between these percents. And notice this is a population proportion. It is not the sample. Any questions on this? Okay, we can also say that if we want to interpret the confidence level, then it's the same idea. If many samples of, it was 900 and, let me find it.
906.
Was it 6? I think it was a little higher. 900, yeah, 906, you're right. Good memory. 906. If 906 Americans are collected, then each will produce a unique confidence interval. 95% of these intervals will contain the population proportion of Americans who approve of Biden, of the job Biden is doing. Any questions on this?
I have a question. So when it was the KISS, it will contain the true population mean
Uh-huh.
of the first KISS. Why was that the population mean and this one's the population proportion?
Okay, so there was a survey question for the KISS. Do you remember?
What was the survey question?
Question. Uh-huh.
I don't remember the exact words.
It was how old were you when you
Ages.
experienced, right? And if you look at the answers, there were a bunch of numbers. Quantitative. Means are for quantitative data. Whereas for this survey, the question is, do you approve of Biden's, of the job Biden's doing? And you don't say 34 or something, you say yes, or you say no.
Qualitative.
Yeah, and it's special qualitative, it's a yes, no question. Got it? So this is a yes, no question. And that you asked a really important question because it's one of the biggest errors people make on the next exam and the final exam is not paying attention to, is it a yes, no question or is it a quantitative? And this course basically is split into those two types. Got it? Okay, so good question, and you need to get that down. So always ask your survey question. What is a survey question? Is the answer a number or is the answer a yes, no for the survey question? If it's a number, then we're talking about a mean. If it's a yes, no, we're talking about proportion. Got it? Okay, so now.
One moment, please. Or
Okay.
don't take that away.
I won't.
So I have a question about the wording in this
Mhm.
paragraph here, this statement. So the necessary words are with, all, and you
So
have to state the sample size.
Okay, so
Right.
first thing, there's two different things. Let me put a space so we know there's really two different questions. So there's the first one, which is interpret the confidence interval or state your conclusion. The second is interpret the confidence level. Got it? So if it's interpret the confidence interval, one thing you have to do is you have to emphasize, you talk about the population, and you could either do it by the population proportion of all Americans or this percent of all Americans. If you don't know the word all, you're in trouble. Got it? And so those are important words. With is important. Whereas if it's interpret the confidence level, if is the first word. Okay, and always if many samples. Does that make sense?
Yes, and then when you're describing after Americans are collected, you have to say, produce a unique confidence interval.
Right, and that's why I showed you that picture of a bunch of confidence intervals, because if you grab a bunch of confidence intervals, some of them are going to get the mean and some of them are not, right? Some are winners and some are losers. Does that make sense? So each one's going to have a different confidence interval. Some are going to be winners, some are going to be losers. 95% will be winners. Okay, but I do need to move on because we only have so much time. And here's the next question. I'm going to go back to the age of first kiss. Okay, and can I scroll a little bit? Okay, so, and in fact, oh, I think I don't even have it here. Let me write down S was equal to, is it that one? Nope, that one. 2.7 about. Good enough for me. So now I have a new question. And I've mentioned this when we did this. I said you'd never do this as a study. One thing, the sample size is too small because it's under 30. The other, if we looked at our confidence interval, even with a 90%, it's between 14.3 and 18. That's a really wide range. Do you agree? So here's a new question. Suppose you wanted to do a new study with a new sample to find out the age of first kiss with a margin of error of no more than plus or minus how about a half a year? Right? Because again, 14 to 18, that doesn't tell us very much, does it? Do you agree? But if we're within a half a year up or down, then you got a better idea of when people are getting their first kiss. Do you agree? Using S equals 2.7 for an estimate of the standard deviation, because that's our best guess, right? How many people do we need to survey? Any questions on the question? Okay, so now what we have to do is we have to realize that we have the standard error. And the standard error is, if you remember, sigma over the square root of n. Do you remember that? So that was the formula for the standard error. It's very important. Well, if we're looking at a 95% confidence interval, then it's going to be sigma over root n times however wide you get because of that confidence interval, that confidence level should be the margin of error. That was from that picture we had. So in particular, let's write this down as an equation. Our error is equal to, and I'm just going to call this Z sub C. In this case, C is, let's see, did I write down, let's say, how many people do you survey for a 95% confidence interval? So C is 95% in this case. And then times sigma over the square root of n.
Can you scroll down a tiny bit again, please?
Sure. Any questions on the formula first?
Yeah, can you go over it real fast again?
Okay,
Now
so-
that we've written it down.
E is a margin of error. Z sub C is the Z that corresponds to 95%. So you draw your normal distribution curve. You go out with a 95% confidence, and then you look to see how far away from zero you have to go. What's the Z score to get 95%? And we've learned actually from the empirical rule, Z score is around 2. Do you remember that? Because two standard deviations away contains 95% of the data. Okay. It's actually about 1.96 is even a better estimate. You don't have to memorize this or anything, but I just want to mention that. Sigma, our best estimate is 2.7. So let me start writing this down. So E is our 0.5, because that's given, because we want a margin of error of no more than 0.5. Z sub C is equal to, turns out 1.96. It's about 2 standard deviations, because that was our empirical rule. Okay, or you could do an inverse norm of 0.025. Remember that middle stuff? Remember that middle problem everyone had trouble with? 95% in the middle, 5% on the outside, 2.5% on the left. And then if you take the inverse, if you use 2.5% or 0.025, and then find the Z that you get, you'll get 1.96. You'll get negative, but it won't matter in the end. You'll see that later. Okay, and then N we don't know. Do you agree? Sigma we do. So sigma, which is S in this case, is equal to 2.7. All right, so there are 2 choices. One is we can plug these in and solve for N. Do you guys want to do that? Could you do that? Do you know how to do that with algebra?
Sorry, I'm a little bit lagging behind with the writing part still.
Okay, if I plug all these numbers in, do you know how to solve for N? You can have a root N in the denominator. Do you remember the algebra you have to do?
Could you explain it?
I'm not going to. I'm just going to ask you. There's a reason why I'm not going to explain it. But can you imagine doing the algebra? That's all I'm asking. I'm not saying, will you do it? Okay, so I got a little bit in trouble for this. So you'll be happy, but some instructors were not very happy, is that I made it easy for everyone. Some instructors wanted the algebra done. And I'm like, yeah, I don't know. I'm tired of marking off too many points. So I created, as you might guess, a calculator. What number do you think it is?
9.
Good guess, but 9 will find the confidence interval. It's not what I'm looking for.
11.
Yeah, it's 11. I'm looking for a sample size. So if we do sample size for the mean, Then sigma was 2.7, if I remember right. Our margin of error was 0.5. Our confidence level was 0.95. Everyone good with that? Have I lost anyone? And I hit calculate N. Or you could do the algebra. You choose. What do you think is easier?
Calculator.
Yeah, like I said, some people got upset at me. And the people weren't the students, by the way. The people were faculty because I made it too easy. So you guys get the easy way. And 113. So what this means is that if we wanted within a half a year for average age of first kiss for a confidence interval, we need to survey 113 people. Any questions on this idea? Any questions? Okay, and that's all there is to it. And what it does, the calculator does the algebra for you and it solves it. Okay. Is that clear? Okay. Something I didn't do, and I think I want to, because we do have a couple minutes, I can do this, is we didn't check the work of Gallup. You want to check the work?
Yeah.
Okay, so again, there were 906 adults. 57% like approve of Biden's job, right? Or how Biden's done his job. And we want to find a 95% confidence interval. Okay, and let's see if it really is plus or minus 4%. Let's check their work. Okay, and I found they don't always get it right, by the way. So don't just say, oh, they're Gallup, so they're going to have it. Sometimes they don't, but we'll see. So let's do it. And what I did, as you might guess, is I created a calculator for it. What number do you think? Today's a lot of,
9,
huh?
10.
9.
It's not number 9. Remember, the survey question was, do you approve of Biden's work that he's doing, or how he's done his job?
Maybe
12.
It's 12. It's proportion. You have to get down. Are we talking proportions or mean? Or are you going to get nailed in this class? Okay, it's very important. Okay, and it's going to happen for the rest of this class. We're going to have 2 main types, yes or no questions and quantitative. And then we're going to have 1 week where we do the qualitative, not yes, no, like what's your favorite color. But most of this class from now on is going to be yes, no, or quantitative. Okay, so in this case, it was 906. How do I get X? Any ideas? Because they didn't give us X.
0.57 times the sample size.
Exactly. So I can click scientific calculator and I put this in because I realized that was needed. So 0.57 times 906. Okay. And you should always do rounding, by the way, because you can't ask 516.4. You can't have 516.42 people. Does that make sense? Okay, so you can't have that many people say yes. You have to have it has to be in an integer. So I'm going to write 516. Any questions on that? Confidence level, Gallup said is 0.95. And I hit calculate. And guess what? 53.7 to 60.
They're close.
Yeah, so if you look at this, by the way, if you subtract 60 minus 54, what do you get?
6.
6. And 6 divided by 2 is 3. So there is actually a little bit higher. They said plus or minus 4%, and it's a little bit less than 4%, a little closer to 3%. Any questions on that? So as I mentioned, Gallup usually overestimates the error, but it's actually plus or minus 3%, not 4%.
What
Any
does the P with a hat mean again?
P hat is the sample proportion,
Okay.
which you can see was 57%. Right, because that's what we started with. So that's P hat. And again, we don't do Greek letter stuff because the Greek letter of P is pi, and that's totally confusing. So that's why they went with the hat. That was about 20 years ago when they switched to hat. Any questions at all on this example? Okay, one more question. Kind of two, but we'll do it together. Suppose you wanted to find out the proportion of college students who approve of Biden. Okay. Now, that might be different than the whole population of America, right? So we can't just say, oh, well, we know it already because Gallup did it for us. Do you agree? But we have a best guess. So we're going to start out with a preliminary estimate of 57%. If we wanted a margin of error of, let's suppose, plus or minus, or at most, about 2%. And using a, how about a, just for fun, 88% confidence level. How many students must we survey? Any questions on the question? Because it's real important. When you're planning your study, you got to decide how many people you have to ask. And this is how you do it. Okay. So what we can do, and I don't have time to do the full formula like I did with the mean, but there is a formula. Remember, it had that PQ over N, square root of PQ over N, happened last week. And that was a standard error. So you have a Z times the square root of PQ over N equals C, and then you solve for N. And it's messy. And do you trust me, it's messy? And you end up getting a formula, which we don't need, because what did I do?
Made a calculator.
I created a calculator to make it easy, even though some faculty got upset at me. You won't be upset, you'll be happy. So first thing what I like to do, it's always a good idea, is that our estimate was 0.57. Our margin of error was 0.02. Our confidence level, CL for confidence level, is equal to 0.88. Okay. Any questions on that?
I'm sorry, yes, I have a question about the margin. I was talking to my kids at the same time, but the margin of error is 2%. So you would, I mean, I'm sorry, so
I turned
I
it
thought
into
the
a-
margin of error was the confidence.
The margin
interval.
of error is how far from the proportion your upper and lower bounds will be.
Oh, okay, got it. So with the plus minus on in the article, that's what was the,
Yeah,
Margin.
so in the article, it gave 4%. And we want to be more certain. We're going to go for 2%. Okay, yeah,
Got-
we're going to survey more people, but hey, we got time, right? Okay, any questions on the idea here? Okay, so then we go back to the calculator. What number do you think we're going to use?
Number 13.
Yep, number 13, sample size for proportion. Again, you don't have to do the algebra. Other classes you do, by the way, but not mine. And notice there's a button, no estimate for P, have estimate for P. Do we have an estimate? What do you think?
for the population?
Yeah, do we have an estimate?
Preliminary
No.
estimate 57.
Yeah, we do have one. So that's a yes. So we have an estimate, and the estimate was 0.57. Our margin of error was 0.02, and our confidence level was 0.88. Any questions? And I calculate in. So now I need to survey 1,482 people. Any questions on that? Okay, what if instead I decided that college students are totally different than Americans, than regular Americans? So this estimate is useless. Does that make sense? So in that case, we hit no estimate for P. And notice now it doesn't even give you a choice for P. And if I calculate N, it's higher, 1511. So having the estimate actually helps. It makes it so you have less work to do. Because remember, just doing a sample of a little over 30 was hard enough, right? For a project. Imagine having to survey 1,511 people. Okay. If I had to do it, Biden will be termed out by the time I was done. It would take forever for me to find 1,511 randomly selected people. Okay, so just note that you got to be worried when there's a big N like that, because it's a lot of work. And if you have a company, it costs a lot of money. So I need to survey 1,511 people if I didn't have an estimate. But even with the estimate, it was still a lot, just not quite as high. Any questions on this idea? I need to do something. I need to go online and not show you what I'm looking at. So I'm going to stop my share and give me a moment. Just a second. Sorry.
I have a little question just to kind of recap some information. When we were first talking about the confidence interval, I wrote down, because I thought you had said that the confidence interval is equal to a margin of error. Is that correct?
No.
Okay.
No. So the margin of error is half the width of the confidence interval.
Got it.
Okay, now I can reshare my desktop. I was too busy grading your test, believe it or not, that I didn't prepare your the next thing. What's the next thing I got to do? I got 2 minutes left.
Secret word.
Yeah, and I forgot to check what I wrote my secret word of. Now I know it. So let me share so you can do it. So the secret word.
Interval.
That's a good guess. I think I've used that one in the past.
Yeah, you used it in the prep for stats class.
Ah, okay. This one is width. And that's because, why do you think it's width?
Because you have to include with when you're talking about the confidence interval.
Yeah, and not only include, but it's the first word with 95% confidence. So it gets you going, it gets you started. And if you get started, that really helps. hard to know where to go if you don't know where to start, right? So the secret word of the day is with. And now I think I can stop the share. But hopefully you understand how important confidence intervals are. And I want to let you know there's two main things in statistics when it comes to using samples to kind of get an idea of the population. One is confidence intervals, and the other happens next week. And those are the two biggies. So this week and next week are the big weeks for the rest of the quarter. And then for the rest of the quarter that we're going to be doing confidence intervals and next week's called hypothesis testing. So now everything is useful. Hopefully you agree. Today was kind of, used a lot. You often look at confidence intervals. Okay, in research especially. And the more we get into this class, by the way, as we go week by week, the more research oriented it becomes. Instead of showing general public stuff, now we're going to get into what you're going to see in your upper division classes when you go to your university or the next level that you're going to move into. So you're going to see confidence intervals there. You won't see it just in everyday conversation, but you'll definitely see confidence intervals. Okay, does that make sense? Okay, so for example, right now, the vaccination, because I just got my next big news. Any guess what my next big news was? Personal news.
Did you get the second one?
I got my second appointment, and it's for the 22nd. So by the way, the 22nd is a webinar night, I think, if I remember right. And so if I'm like out of it, you'll know why. Because that means I got vaccinated and I had a bad reaction. Hopefully it doesn't happen. Hopefully I'm not totally tired. But so the question is, what's the percent effectiveness of the vaccination? Anyone heard? What they're giving is 94.6% for the Moderna one. And that's what I'm getting. And what I haven't found online yet is what the confidence interval is. Does that mean, 94.5 to 94.7? Or does that mean, I don't know, 90 to 98 something? Does that make sense? And I actually haven't been able to find any information. If anyone can find it, that'd be cool. In fact, you can post that up on your discussion thing. Because you have an assignment due on that for the post. But I'm excited about it because I got the news less than an hour before this webinar. So I'm going to stop the recording.